This is NRCS's Rainfall Simulator. I actually like to really call it's a soil quality or soil health test. And really what we're going to actually do here today is really look at a number of different soil characteristics. We'll talk about those a little bit more. This demonstration is really set up to look at several different soil or management type situations, and then look at infiltration, aggregate stability, look at erosion, runoff, those parameters associated, and we'll talk some more about what they actually mean. And as Dave Stephan was talking earlier yesterday, that at some point you need to make sure you understand what those terms really mean when we start talking about hydrologic conductivity or permeability in conjunction with infiltration. Just to go over this a little bit today, how this thing actually works. In the next 15 minutes or so, we'll put on about 1.5 inches of water on these samples, and it boils down to this: is each one of these trays is set up in a different management condition, and in essence, what we've done is take a piece of grass, or in this particular case, some no-till soil out of a field and conventionally tilled soil, put those in a tray. And what we're going to actually do is we're going to collect either the runoff or the infiltrated water. In other words, the water that's moving through, moves into the soil, moves through that soil profile, and goes into one of these jars. So let's just talk about this for a second. Any water that hits this tray and runs off will go through this funnel and end up in this front jar here, right? Any runoff water or sedimentation, etc. Now, each one of these trays is set up with a tray underneath it also, so that any water that's moving through the soil profile that we've cut out here will actually move into the back jar that you see here. So each one of these is set up to do just that. So what exactly do we have here? Well, what we've done is gone out right here, and on this clay site, it's collected basically it's a blue grama beat up cross fence sample, and you'll see how that reacts. When we get out of the field here, we'll actually do that in an infiltration ring. We stayed on this side of the fence, and you can see those patches of big blue stem. So we cut out one of those. Side-by-side comparison. Now, what I also did is, because I have access to a number of different soils, what I did is I actually collected, this is East River, a no-till soil. And actually, this is just dug up, put it in the tray. So you're really looking at parameters of aggregate stability instead of macropore development. We'll talk some more about that. But anyway, you're looking at that condition, and it has some straw on it to simulate that surface cover. What I also did is I said, okay, what is that soil like without that surface cover? And then what does a conventionally tilled field look like? In other words, right down the road from my place, I actually collected one of the neighbors' fields, and that's what you're looking at right there. So conventionally tilled, no-till with no residue, no-till with surface residue, straw on the surface, big blue stem, blue grama, right? Okay. Well, let's turn this thing on and see what happens. So back to what I was talking about a minute ago, is if that raindrop hits the soil surface, it goes through a process of what we call detachment. That soil particle is then, that soil pad is actually broken up. That process of detachment occurs. That soil actually bounces up quite a bit actually into the air. You can see that in this depiction over here of a raindrop hitting the soil surface. You can see that soil actually bouncing up here. It's not doing that here, right? So we've got that process of detachment actually occurring. That soil is bouncing up in the air, and then it can actually go into a process of what we call transport. And that transport might be either very locally deposited, or it might be, frankly, off-site deposition. So that process of detachment and transport we call water erosion. So that's what we're actually talking about. And for those of you that are watching the demonstration and not paying attention to me, you're probably learning more. So I continue to do that, but that process of detachment, not only does it cause erosion to occur, it causes something else to occur. It actually causes that plugging of the soil surface so that we stop infiltration. In other words, that soil particle is broken up. It actually then moves into what? The pore space that's available and plugs that soil surface, increasing what? Runoff and decreasing infiltration rates. So how can we circumvent that process from actually occurring? Well, we get something in the way. We can either call that surface residue, duff layers on the soil surface, or canopy associated. And what happens is if that actually occurs, then we do what? We limit runoff and increase infiltration, right? So that's really what we're talking about. Now, there's something else I guess I always kind of like to really talk about too, is what is the composition of soils, and just talk basically about that, is that when we look at soils, we're really talking about something that's about half mineral material, 40%, 45%. Part of that's organic material, but about 50% of our soils is what? It's pore space. It's either filled with air or water, all right? The other thing that we need to keep in mind is that when we start talking about organic materials within our soils, etc., that can be anywhere from 2 to 6%, something like that. Keep in mind just this, though. 2 to 6% of that surface horizon that we're actually talking about, but approximately 5 to 10% of that is actually living, microflora and microfauna. And I'm not talking about roots of plants. I'm talking about things you can't see. So let me do some math for you. Let's say we have a soil that has a 4% organic matter in the surface, right? On a 2 million pound acre furrow slice, that gives me about 80,000 pounds of organic material out there, right? If that was 10% living, that's about 8,000 pounds, or about 4 tons of it you can't see is living, right? So there's a phenomenal amount of soil life actually occurring. Now, let's go back to the demonstration here a little bit, and let's just catch up a little bit. Anybody learning anything here yet?
Where is the water on the no-till to black dirt? Is that stuck in the dirt, or where is that water at? It's not on top, you can't see it in the pan. It's not in the first jug or in the second jug as much as it is in these other jugs.
Well, basically what we're actually seeing here is this conventionally till over here is doing what? We're seeing runoff and no infiltration. The no-till one here is infiltrating and no runoff. The second one is infiltrating.
On the no-till one, there's not nearly, is it just infiltrating slower, or, I mean, there's not nearly as much water in that second back jug as there is in the middle back jug.
Which one are you pointing to? This one or this one?
Well, I'm comparing the two.
This one's not as much water as that one.
Okay. Good. It's a good question. It's got to be there someplace. It didn't go anywhere. It's still there.
I guess what I was asking is that also creating a crust, and it's just taking longer? We can't quite see it yet?
Well, at some point, what's going to occur, at least typically what occurs, is that you're going to actually find that even though that no-till soil has pretty good aggregate stability, it hasn't been tilled and broken down, eventually it will actually then start to break down, and what I just talked about before, those soil particles will detach, and they will start to plug up the pore space, and it will stop infiltrating water and start running off water. And we'll see if that actually occurs here today. I always get a kick out of it is people think that we really just kind of make this up and whatever else, but every time we run this thing, we have relative ideas on what actually should occur, and then sometimes we get thrown off. What it always gets me here is the other thing you need to understand. These are both clayey sites. These are loamy. So if they were all loamy sites, we should actually have this stuff infiltrating even more or running off even more than the loamy site. So
one thing that I'd like to point out is this jar right here is just starting to run over. So every drop of water is being infiltrated into the soil there. And that's around somewhere between 150 to 200 pounds of grass is grown with every inch of water you get in the soil. So you're losing a lot of grass here, and that's capturing it all there.
The wind's blowing over there too, but you can see that as an example, something that has really good biological activity. You can see the pore space in there. This is conventionally tilled. This is a no-till clod. That's that soil you were looking at. You can see that looks like a sponge. So really kind of a really fun demonstration I like to do is as you put a clod in the water, just submerge it. See the air coming out? Remember I talked about half of it being pore space? Same thing happens with a conventionally tilled clod. But the interesting thing is if I could have you just hold on to that for a minute here. You hold on to that one too. We'll look at those in a minute. What you're going to actually see here is what a term we call aggregate stability. And that aggregate stability has to do with how well those soil particles, that is sand, silt, clay, are actually bound together by glues, gums, etc. Some of those products we actually know something about. One of those happens to be a glycoprotein called glumalin. It's shown here green. It's actually brown in soils. It's stained green. But that glycoprotein is actually produced by mycorrhizal fungi in soils. And you can see here that in this particular case, you see that clod is actually sloughing off on the side, just on its own. Because we've tilled that soil, we've actually removed, in other words, oxidized or mineralized that organic material that we know that's sticking those soil particles together. You say, well, what difference does that make? Again, we get back into infiltrating water. If your soil is not water stable, that water moving through will then plug up those macropores and it won't move as much water down through that soil profile, right?
Residue has just reached the top. Our no-till with no residue, it's caught up almost, but it's not quite there. For some reason it had a slow start, but it's catching up there.
Now it's starting to run off a little bit, huh?
Just a little bit, yeah.
Okay.
And still no infiltration on the conventional till. I think it's a loser.
But anyway, I don't know if you can see this here, is that even compared to conventionally tillage, that this thing's got just a lot of sediment down at the bottom of it.
One of the things that I was told from the time I moved to South Dakota was, well, yeah, that blue grandma sod, it'll run off a lot of water, but the runoff will be clean. I just believed people when told me that. Well, ever since we've been doing this, I kind of thought about that a little more. It's not so clean as you. It's not quite as dirty as this one, but it's certainly not clean.
You tend to get farther east and farther south into more of the corn belt, and they tend to want to till a little more than, say, farmers in central South Dakota or northern South Dakota. I realize their soil is different and the way they can grow it is a little different probably, but this still has to apply to them. Why are they still tilling? Is it too much topsoil cover or too much organic matter on the top, or what? Why are? Oh, I can answer that.
See, and that's kind of the interesting thing. It's a really good question to ask why. I'm still doing that today, and we need to try to get people to think about other strip till methods, cover crops, something to break down residues so that we can get in early enough in the spring on cold, wet soils. So, anyway, one of the first things I like to do is talk about this for just a second. Is conventionally tilled, everything ran off, right? A lot of sedimentation, etc. No-till, a lot of infiltrated water, started to run off, right? With the residue, ran off a little bit, a lot cleaner, right? This is the impact of residue. That surface residue impacting stopping that detachment process. When people start talking about the cellulosic ethanol, and you've heard about this, we're going to remove residues and we're going to make ethanol out of those too. If we remove all the residue, does that affect our runoff and infiltration rates, etc.? Yeah, it does. So we really can't do that. The cool thing that I find over here is that these are kind of the extremes, but these are, again, clay sites. How much water did you run off? The interesting thing to me too is if I threw a cover crop flat up here, in other words, grew a cover crop out in one of these, it would look very much like this one. And then we could go to and start asking, why does the government spend a lot of money on funding and promoting cover crops? in this state. Well, that would be why. It's not only limiting runoff, but just how clean it actually is. Anyway, before I get done here, I guess I'd like to say that I didn't quite put on as much water as I wanted to. We got about an inch out there. I have problems with one of my pumps, believe it or not, on this simulator. When we got
Doing that, we believe because it's so dry on these clay soils, you get some major cracks, and that's probably why we got as much infiltration as we did.
and it really shouldn't occur like that at all. So
Normally you wouldn't even get that much.
anyway, if we start looking at this no-till soil, you can actually see that you know, we put a lot of water through this thing, and it should be wet to the bottom. That's what you would think would actually occur. What about this one? This is a 2.5 inch or 2 1/4 inch flat, conventionally tilled, right? There's a couple dry spots on the bottom of this one. I'm surprised it actually got as wet as it did. There's a lot of cases it was completely dry on the bottom of these things.
Normally it's just powdery.
So, in other words, if you're not infiltrating that water, it's running off. It's really that simple. If you're plugging that soil surface and the water can't move into those macropores down in the soil profile, you're done. If you have management conditions that are conducive to limiting that macropore development, in other words, those larger pores could be insect cavities, etc., moving down through that profile, you're going to infiltrate less water, you're going to produce less grass. Eventually, we'll start talking some more about that, but you're going to end up with less organic matter in your soil profile. It's going to go away, and again, it's a cyclic process of less production out on your field. It could be, like I say, within any of those rain sites, we're going to actually produce less biomass because we have less organic matter. In other words, less nitrogen within that system in that soil. And we'll look at that a little bit later too. So anyway, I really like doing this demonstration just because frankly we can get across some really good concepts associated with water movement, hydrologic conductivity through soils, sedimentation in a fairly short period of time. So I guess I'm hoping that you take something home from this, is that not only is we start talking about a cropland standpoint, but from a range management standpoint, we can drastically affect how much water that goes into our soil profile. I don't know if Dave Steffen's out here yet, but he said something about creating your own drought. I think that's actually the case. So your management can drastically affect water movement on your place. Go ahead.
We see a lot more runoff with the blue grama versus the conventional tillage, but they are different soil types. So is that different solely based on the soil type?
Well, you know, and I hate to do a direct comparison here just because of the drastic differences in soil types. Because I would think that if I had a loamy site with that blue grama there, it would actually have less runoff than even the conventionally tilled. So.
If it drains down through that soil, where do you want that to end up? Is that going to go back in the groundwater and come up in a pump, or where does it go?
Well, it really boils down to this: is that how that water dynamics actually works in your soil actually has to do with the soil not just on the surface, and that's all we have right here is that little chunk of surface, but what actually is below that. Do we have a glacial till? Is it a loam all the way down? Is it a clay loam? What kind of water holding capacity does it actually have? So for the most part, what I'm saying is that based on your management and your soils out there, for the most part, it's going to actually probably stay at some point within that soil profile, being able to use that for your next growth spurt, next period that you're going to actually have growth on your paddock. But from my standpoint, you also need to understand from an extreme standpoint, if we ended up with a lot of rainfall that water could no longer hold, it would then slowly move back down into the water table also. So water means production from a rain standpoint and from a cropland standpoint. My point I want to get across is we want to try to keep that water where it fell, and based on that, it has a lot to do with what we're managing out there and how we're managing our rangeland and cropland sites. So.
Yeah, and a lot of times as you get down into the parent material, usually there's a good 3 or 4 feet of soil below there. So, it'll soak into that, and a lot of it stays there. Some of it will go into the ground.
So a question for you guys. A few years ago,
with a different trailer, but it's virtually the same simulator, did this demonstration at the Black Hills Stock Show. And the difference that happened is those guys, it was Tom Quinn and Matt Stoltenberg, and I don't remember who else, went out the day before and got their soil samples, and then they left them in the trailer overnight, and they froze solid. So they kind of represented what would happen in the wintertime when your soil is frozen.
Mm-hmm.
And I was sitting there going, oh, this demonstration isn't going to work this time. It's going to be frozen dirt like concrete. What do you guys think happened? Do you think the demonstration worked, or do you think it all ran off because the soil was frozen? Worked beautiful, exactly like this. And that conventional till did what he was expecting. It was dry as a bone in the bottom when he flipped it over. But yet the grass ones and the one with the wheat straw on it soaked in, and that soil was definitely frozen. I mean, we played with it, and it was hard as a rock, just like ice cubes.
And I guess I'd like to add to that. When we start talking about water movement in frozen soils, it actually really has to do with water content before it actually freezes. So if these soils are fairly dry, they will still infiltrate water. If they're not, however, if they're wet, you can imagine then that ice actually freezes in those max pores we keep talking about. It will actually plug and stop infiltration. So getting back to your example, is it, you know, I was trying to think about where he was, and in a dry sample it would infiltrate water, where in a wet sample it probably wouldn't. I know that a lot of us have been taught, at least maybe from our dads or maybe from just production, that going out and doing tillage is actually going to infiltrate more water. That's just not true. The opposite is actually true. You're going to actually plug more of those macropores, and it's going to eventually run off. So, and this year was a good example for me. As you go out, and anytime we got a rain event, go on a no-till field, a conventionally tilled field, and you could actually see the conventionally tilled would actually go down, the water start to soak in, it'd be hard underneath again. Where no-till actually was drier on the surface because it was moving that water rapidly down through those big pores back down to the ground further. So it was really kind of, well, it was a lot more fun digging in the no-till field just because it was moisture down further in that profile.